Welcome back to ECE 320A. Very important class. It's the last class. Obviously you have a final, but that's not Thursday, that's Friday, and it's this week. I hope that doesn't surprise you. Your final exam is at 1 o'clock in this room on Friday. To get you ready, we are having a review session this afternoon in a few hours. That's at 4 o'clock, and it was hard to try to find a classroom at that time that was available, but it's in Saguaro Hall. I think you maybe all know about or where that is. I hope you can find it. It just recently changed, well, in the last 4 years, maybe its name. It used to be called something else as far as the building, so I'm not used to calling it Saguaro Hall. Maybe you are. It's probably always been Saguaro Hall since you've been on campus. That's in room 225 today. Teacher course evaluations. I'm so far a little disappointed with the percentage of responses. Maybe everyone here has responded, but that's about it. Meaning it was under 50% when I checked yesterday. I didn't check again today, but that's, and somebody was wanting extra credit, and I said 100%. It's looking less and less likely that that might happen. Homework 10 is due tomorrow, not today, but today's class should give you the material that you need to finish or complete homework 10. That's on filters. You should already be able to do the first problem based on previous material, essentially last lecture's material. And for that reason, let's try to get through a lot today. Meaning we'll quickly scroll through the process for the final exam. Today what we want to do is talk about creating more versatile filters, changing their bandwidth. That means frequency scaling the transfer functions. If we now have a nominal transfer function with a bandwidth of 1 radian per second, how do we change that frequency so that it's maybe 4,000 hertz, for example? And you do have to worry about the difference between hertz and radians per second. If you want more filtering, by more filtering I'm meaning maybe a sharper roll-off in the stop band, meaning it's a steeper slope, and you know how to get a steeper slope. Yes? Just keep adding more and more orders or higher and higher orders, and we'll go through that today. Yes?
The example that you put up is that.
So the question was, the example final or the practice final was multiple choice. You might anticipate that again Friday. Just thought I would throw you a curve at this point in the semester. Okay, but show your work. If there's no how, it does if I look at your work. So it's easier for me to find your answer if it's multiple choice. It's for me, obviously. I have to get these graded and turned around quickly. So show your work, and I will have partial credit on a multiple choice exam. So that it's a little weird, huh? So don't try to figure that one out, but basically make sure you indicate which answer you're leaning towards or wanting to circle. Okay? So it will be multiple choice in that you have to indicate a particular answer for that problem. Yes? Well, then the question was, if you get the right answer but your work is not consistent with your answer, then I will start looking at your neighbor's papers and comparing to see if you got your answer from theirs. I don't know. Hopefully that you will be consistent. Yes?
Will we be marked off if we don't show work?
Yes. So the question was, if we don't show work, will we be marked off? I would prefer that you show me your work so that I can see where you're going or not going relative to, you'll get more points if you show your work. You're going to have to do some work. And unless you are guessing, and I wouldn't put my hands in your guess, okay? So I would show your work on the space provided and indicate the answer that's consistent with your work. Wow, I was hoping to cover a lot, and one question opened quite a can. Where did we get to? Butterworth Filters. Now we're on to pancakes. Hopefully everyone make sure you get a good breakfast on Friday, a lot of sleep the night before. Today we will talk about a generic second order section. That just means a second order filter, which earlier in this semester somebody said, can we actually design a circuit based on a transfer function? Now you can. If somebody now says, I need a fourth order filter, and we'll figure out how to calculate the order of the filter that we need. Now if I need a fourth order filter, how do I build that? Well, I just put two of these second order sections together. I cascade them. If I need a fifth order, I have the two and I add a fifth. The coefficients will obviously be changed, and we'll have a table for determining where those Butterworth coefficients need to be in order for those circuits to produce the transfer function that you want. And we'll go through some design steps, and hopefully we'll get through a third order Butterworth low-pass filter example. That's the idea. Final exam. 4 sheets of notes. Don't put your work on your notes. Put your work on the final exam. A calculator and something to write with. There is a practice, and it apparently has been looked at by at least one student, maybe more, and you might look at that to get some clues, but it's a comprehensive exam. We've covered enough material to give you 15 different problems on the semester material. There is a list of topics that you can refer to, and after tonight's lecture there will be notes and a video from the review section, and the feedback that I was getting is 3-phase power and Bode plots. So we'll probably spend our time tonight with 3-phase power and Bode plots. It's not really tonight, it's this afternoon, it's at 4. Filters. Let me scroll through some information or material that you already should know. If I now said, give me and now we're talking about how do we change the bandwidth and what happens when we increase the filter order. Can we just stack a bunch of these similar looking filters together and achieve the result that we want? And the answer is no. We have to be a little bit more careful with how we select those poles, and that's where Butterworth comes in. Butterworth pole locations are very important, and we'll try to justify that. But if I said, give me a first order filter, low pass, the pole zero diagram is as simple as one pole right at s equal to minus 1, which has a transfer function of 1 over s plus 1. If we said, what's going to be the magnitude of that transfer function? What's the magnitude of h of j omega? Now, what are we doing when I say the magnitude of h of j omega? Do you have a picture of what you might be doing relative to that S-plane plot? And now you can just remember me walking up the imaginary axis. And where do I need to walk up to if I'm looking at the frequency of at cutoff? What is the cutoff frequency or the break frequency in this transfer function? 1 over s plus 1. The pole is at minus 1, the break frequency is right there, at omega equal to 1 radian per second. So we walk up the imaginary axis to J1, and then we look at the distance, we measure that distance, that gives us the magnitude contribution of that pole factor in the denominator. And we're dividing that into 1. We want to know what is that transfer function's magnitude at omega equal to 1. We're really just evaluating h of j omega when omega is equal to 1. And we're replacing s with j omega. So that the only thing that's changing is that S downstairs is changed to a J1. That's where we are on the imaginary axis, and we find the magnitude of that ratio of polynomials in S. What's the magnitude of the numerator? And that won't be a multiple choice question on the final. That's a gift, if it was. What's the magnitude due to the numerator? 1. You have a complex number that's just all real. It's 1, and you're finding the magnitude, that's 1. Then what's the magnitude of the denominator? Now you can think of that as the hypotenuse of this right triangle with a real distance of 1 and an imaginary distance of 1. Yes?
Is the gain the numerator? Is that like the coefficient?
So the gain, the question is, where's the gain, or what is the gain? And you have a gain at all frequencies, don't you? But people use that term maybe inconsistently, but ideally if you said, what's the gain, you would say, okay, let me put this transfer function in time constant form, and what's the coefficient or the constant that comes out independent of all of those other factors? And that would sort of be your gain. In this case, what's the DC gain of this transfer function? 1. And that at DC is as big as the magnitude is ever going to get for that transfer function. And now we're trying to find this magnitude at the break frequency, or right where the pole is located. And I think you can find the hypotenuse of a right triangle. That's why you took all of this high-powered math in grade school. You learned about triangles, didn't you? Right triangles. I'm being a little facetious, but now we can do the square root of the real part squared plus the imaginary part squared, and that's 1 squared plus 1 squared. So we're at 2. We're taking the square root of that, and we have then a magnitude at cutoff of 1 over the square root of 2. Yes? So now the question was, is the gain in terms of decibels? Is it the absolute gain? It could be either. So you need to know what is the gain being requested of. We could say, what's the gain in absolute terms? That's 1 over the square root of 2 at the cutoff. So now we started at 1 at DC, and now we've rolled off down to 1 over the square root of 2 at a frequency of 1. And that's because that denominator factor is continuing to get bigger, isn't it? And we're dividing 1 by that bigger and bigger number. I'm showing you the hypotenuse. I'm not directing the choir, although I could be. And what are we doing? We're getting higher and higher frequencies, aren't we? Which is maybe what that section needs to be giving me. So the magnitude could be asked in absolute terms, or it could be in dB. If we find it in dB, we take 20 log of that number. In that case, if we go ahead and do that very, very lengthy, I'm doing it in as much detail as possible. A lot of times you'll just see, oh, that's minus 3 dB. I'm trying to explain where that minus 3 dB is coming from at the cutoff. We're taking 20 log of 1 over the square root of 2. Square root of 2 is in the denominator. That gives us a minus 1 as an exponent. The exponent in the argument of a log can be brought out front as a scaling factor. We now have minus 20 log square root of 2. Square root is 2 raised to the 1/2. That 1/2 now can come out in front, and now we have minus 10 log of 2. And what have you memorized? The log of 2. That's 0.3. So 10 times 0.3, again, another hard math problem, minus 3 dB. So if somebody says, oh, what's the magnitude at the cutoff? You could say, oh, it's 1 over the square root of 2, it's 0.707, it's minus 3 dB. All of those answers are correct. They're consistent. You just might be asked what type. Is it absolute gain or is it in dB? And then you would know to distinguish between 0.707 or minus 3 dB. Is that clear? That should all be review. The cutoff frequency is also called the half power frequency, and then we put on our 2-year-old hat and we say why. Where is this half power frequency coming from? And that's what I'm trying to demonstrate here. The transfer function or filter is what processes the input waveform, and that's what's described in V naught is equal to H V sub I. That's how we find the output. And we know what H of S is. That's 1 over S plus 1. But what's power? V squared over R in this note. If it's real power, it's VI, isn't it? If it's complex, here's another review. If I said, what's the complex power formula? What is that? VI star, isn't it? And those are phasors. And without that 1/2 factor, you're representing V and I in RMS units. So the complex power S is VI star. But here, we're just looking at the real part, and that's proportional then to V squared. If we square both sides of this V naught equal H V sub I, then I hope you see that what we start focusing on is what is coming out of H squared. If we look at the magnitude squared of the transfer function at the break frequency, then we have 1 over the square root of 2 squared, or 1/2. We've cut the power in half from the input to the output, because V sub I squared is getting scaled by 1/2 to produce V sub 0 squared. So somebody might say, what's the half power frequency? And in that transfer function, you would say, oh, that's omega equal to 1. They might say, what's the break frequency? What's the cutoff frequency? Those are all consistent questions. And they are all answered with omega naught equal to 1, or omega sub n is equal to 1. Questions on that? Oh. So let's continue. Now we'll slow it down a little bit. That was trying to give you a feel for these cutoff frequencies, the half power frequency, etc. What if we wanted a different bandwidth? Because the bandwidth is typically determined by this 0.707 or 1 over the square root of 2 or minus 3 dB point in a low-pass filter, or the half power point frequency. What if we do want a different bandwidth? What did we talk about last time that we could do to a normalized transfer function or to impedances? We could magnitude scale and we could frequency scale. In this case, if we want to change the bandwidth, that's a frequency, you would expect that we can now frequency scale the transfer function. Let's look at what that might yield. Let's start with a normalized transfer function. And that's a low-pass filter. And what's the bandwidth? That's out to our half-power frequency, or that's out to our cutoff frequency, or that's out to the break frequency. In this case, that's 1. We don't want a bandwidth of 1. Let's say we want a different filter. So the bandwidth is a frequency. So now we're interested in the bandwidth of that. So was that hard to read? Sorry, my Y got a little bit out of control. Yeah, it was kind of mixed up, wasn't it? Luckily, I wasn't texting that, or you wouldn't have really been able to figure out what that was. Yeah, you couldn't have hashtag TF on it, whatever that means. All right, let's now say that we want a bandwidth of 5 radians per second. And we could specify the bandwidth in terms of hertz also. We could have a bandwidth of 10 hertz or a bandwidth of 200 hertz. We can specify it, but we have to be consistent when we do these changes. We now are saying that we want S new to be 5 radians per second, whereas in the normalized transfer function, which I'm calling old, S sub old, that's 1 radian per second. And to frequency scale, we are then saying that we want S new to be some scaled version, K sub f, of the old frequency, or our normalized transfer function was in terms of S old, so now we are really replacing S old with S new divided by K sub f. That's the relationship between what we want, the new frequency, and the old frequency that we had. And you might see a problem like that on the practice final. Let's say you need to change the frequency by a certain amount or scale the frequency. Then that's giving you this K sub f, and you need to now relate that to particular parameter values, for example, that we've talked about last time. Our strategy then is in the old transfer function we replace S, which typically is a normalized transfer function. In normalized filter with S over K sub f, where the S in the numerator of S over K sub f is our new S, and the original S is our old S. So now we've scaled that frequency. In our example, our scaled transfer function I will subscript with an S. This is now for the scaled transfer function, and I want that to have a bandwidth of 5 radians per second. That I can find from the original or from the normalized transfer function by replacing in the normalized transfer function everywhere I saw an S, I would replace it with S over 5 or S over K sub f in general. This is now the normalized. In our case, then, we have 1 over. We started with S plus 1. Now we're replacing S with S over 5. And if we multiply numerator and denominator by 5, which we can always multiply by 1, 5 over 5 is 1, then we end up with our new transfer function that has been scaled to be 5 over S plus 5. What's the DC gain of that transfer function? 1. And what's its 3 dB frequency or cutoff frequency? 5. So we've made our bandwidth wider by frequency scaling. If you needed a low-pass filter with a different frequency, you now know how to change the frequency, the transfer function to achieve the frequency that you want.
And the frequency is just
And the frequency is the location of the pole. And with our Butterworth, it's going to be the distance those poles are from the origin. In our normalized Butterworth, they will all be a radial distance of 1 into the left half S-plane. They'll be on this circle of radius 1, all of our poles for a Butterworth filter. If we scale, we're just expanding that circle to a larger radius. But the angles separating all of those poles will be the same. That's where we're headed. Because right now, all we've done is looked at a first-order filter. Let's do more filtering. Meaning, we may want to roll off or attenuate much more rapidly than a first order. How fast are we rolling off into the stop band in a first-order filter? 20 dB per decade. We could double that by getting a second-order filter, and then we're falling off at 40 dB per decade. We're going much quicker. Yes?
Clarify what bandwidth
The bandwidth, the question was, what is the bandwidth? All I'm saying is that if we had a low-pass filter, then this frequency, whatever that is, let me just say omega sub b, that's our bandwidth. So, if you had a, and this is for a low-pass filter. Is that clear or not? There was another question. So now if you had a bandpass filter, now you have to worry about what you're speaking of. You're going to have a center frequency. So if you had a bandpass frequency or bandpass filter, you really have a couple of things going on here. You have, let's say, a center frequency right here, and you have a bandwidth, let's say, of that pass band. And that would be between these 3 dB points on either side of the center frequency. And this might be your bandwidth of the bandpass filter. But we are, in this class, focusing on the low pass, and so there shouldn't be any ambiguity in the term bandwidth. It's where are we reaching 3 dB in the actual transfer function. It's, well, the bandwidth is from 0 up to that place. So the bandwidth is from DC up to your cutoff frequency. So if your cutoff frequency is at 5, your bandwidth is 5 radians per second. So now if you have a high pass, a lot of times what you will do is you will say, what is the cutoff frequency of my high pass filter? And now you're looking at what frequency do you start passing or favoring high frequency signals. So you might say, I have a high pass filter with a cutoff frequency of 10 hertz. Now you're throwing everything away from, not really, but you're attenuating frequencies from 0 to 10, and now your bandwidth is from, of that filter is from 10 hertz all the way out to infinity. But they probably would specify that as what's the cutoff of that high pass filter. And then you're talking about where am I reaching this break between where I'm largest and where I'm coming up from. Whew. Question?
Yeah, kind of like on a side note, is omega in radians per second?
Question was, is omega in radians or hertz? Radians per second or cycles per second, hertz. I will try to make omegas always in radians per second, and F's will be in hertz. so that omega is 2 pi f. If I talk about hertz, then you need to change that to omegas to do this scaling. And we'll try to do that with some of these examples, if I ever get there. Question?
So if you have band pass, what is, if you have multiple frequencies that you're passing, what's the bandwidth of that? You have to add the two.
The question was, what if I have something like this? Maybe, I don't know, were you doing something like that? Now you have to give the information to uniquely specify that, oh, the low frequency pass band is of this width and it's centered at this frequency. The high pass band is located at this center frequency and it has this bandwidth. So you can't say there's one bandwidth for this mess. Okay? So I wouldn't get too hung up on bandwidth. It's just from 0 out to the cutoff frequency. Let's try creating a second order filter. We already know a first order by just putting together or cascading two first order filters. And I'll read the last chapter to you. I'm setting up a failure. So this is not really what we want, okay, but we're just illustrating what happens. We may not want to just bank or cascade a bunch of these first order filters. That's what I'm trying to show you. But if we did, then we would say, oh, here is a second order filter. It's 1 over s plus 1 combined with 1 over s plus 1. Or this is now 1 over s plus 1 squared. What we want to do now is check what is the magnitude of this at omega equal to 1. Aren't we just putting the same thing on top of each other? Not quite. So that's what we're trying to show. What is the magnitude of the second order filter at 1 radian per second? And we can numerically compute that. We have h of J1. That's now just 1 over j omega plus 1 squared, where we are now replacing omega with 1. Or, again, that's just the square root of 1 squared plus 1 squared, the real part squared plus the imaginary part squared, squared. That's now 1 over the square root of 2 squared, or 1/2. And what was our magnitude at omega equal to 1 in the first order filter? 1 over the square root of 2, or 0.707, and not 0.5. So now our magnitude is much lower at the same frequency because we've put these two similar filters together in cascade. What does this look like? If we sketched this, and now it's not going to be a Bode plot, this frequency axis is linear. Let's say that, and I'm probably not going to be able to draw this very well, but let's say that's 1 radian per second. We're starting here at 1, and this is now h of j omega. And let me say in blue, let's say that's 0.707. Let me see if I can hit that with this. So that's for our first order filter, n equal 1. What did we just see, though, if we had a second order filter that was just a cascade of these two first order pieces? What was our magnitude at 1? So this magnitude was 1 over the square root of 2, or 0.707, and what we just computed was now a filter that has a magnitude of 1/2 at the same frequency, omega equal to 1. And I have here in my notes that this might be illustrated in a figure in the textbook, figure 16 in chapter 15. So that now if we looked at the 3 dB frequency, which is right here, this is minus 3 dB. It's the 0.707. If you used that, and this is not drawn very accurately, but what's the bandwidth of the second order filter? Is it 1? The bandwidth is the frequency at which it crosses minus 3 dB. Does the red line cross 3 dB at 1? No, it's much less, isn't it? So now by cascading these filters, I've now reduced my bandwidth, and maybe that's not what I wanted. I maybe wanted to maintain a bandwidth of 1 and just have faster roll-off in the cutoff. And this is, I do have faster roll-off in the cutoff because I'm now going down at 40 dB per decade, but I've now sacrificed bandwidth. So if I drew this on the final and I said, what's the bandwidth of the second order filter, could you give me a back of the envelope value for that? Do you see that this is the bandwidth of that second order filter? By this, from this sketch, it's where that red curve crosses minus 3 dB. That's much smaller than 1. What I'm saying in that picture and in this example is that the minus 3 dB bandwidth is less than 1 radian per second in this second order filter. And what we may want is we may actually want to preserve no matter what the filter order, it might be nice if every time we looked at the magnitude, no matter what the order of the filter is, it'd be nice if that was always our 3 dB frequency, the 1 in a normalized filter. Maybe that's what we want. We want the magnitude of our filter, the normalized filter with the bandwidth, obviously, of 1, to be that bandwidth as we crank up the order, as we make it a second order, as we make it a third order, as we make it a fourth order. Which means that, do you see that the blue curve is flatter, let's say, than the red curve? In terms of in the pass band, the blue curve is flatter than the red curve. The blue curve is Kansas, the red curve is Colorado. Just joking, but giving you a feel for if you're into geography. I don't know where that's coming from, but I hope some of you are hungry. We are looking now for maximally flat filters, and that's the Butterworth pole pattern. Yes?
So, what is the bandwidth for that?
Right there. The bandwidth of that second order is, let's say, 0.6 radians per second. I didn't calculate it, I eyeballed it. So you said, how do I calculate that? You could calculate that in your transfer function, you could say, let me set this h of j omega magnitude equal to 1 over the square root of 2, and you could back out and find omega. And it will be less than the 1. So you could compute it, but that's not what we want to do. We want to now say, if I now looked at higher order filters, and this is not in dB, so that magnitude is in absolute terms. If I now say, here's 1, and here is now, let's say, the 0.707. Maybe it's not very accurately drawn, but let's say this is now 0.707, or minus 3 dB. No matter what the filter order, we want our filters to go through that point, which means that as we increase the order of our filter, we want this to be flatter, but still go through that point and then really fall off quickly in the stop band. So all of these filters are looking more and more squarish as we increase the order n of our filter. This is in increasing. And here, this is in increasing, if that makes any sense. So we're moving closer and closer, or more and more, to have a sharper transition between the pass band and the stop band as we increase the order of our filter. Here, let's just say that this is for n equal 1. Let's say that's our first order filter. And all filters pass through that 0.707, and when they do, that means that our bandwidth is 1 in all of these filters. Is that clear? Yes.
For that last problem, the second order filter equation and the low pass of like plus 3, and you would tell us the frequency that we're evaluating. Right? So if it said omega equals 1, that's plus 3.
So now the question, I think, was something like, what if we had a transfer function h of s equal to s plus 1 and then an s plus 3? Is that what you're saying? So what's the Bodie plot of that look like? What's the DC gain? What is it? I'm hearing, so if we plug in s equals 0, what do we get? 1/3. So we probably would say, you know what, let's put this additional piece in time constant form so we don't mess up our gain. So we might put this in like that. But you know that that would be an s plus 3 factor, and the 3 would come upstairs, and we have a DC gain of 1 for this filter. But what's the Bodie plot look like? Well, we're flat until we reach 1. Then we're going down at 20 dB per decade, but is 3 a decade beyond 1? No, but it's a little more than an octave, isn't it? And how far is an octave? 6 dB. So at 2, we're at minus 6. And at 4, we would be at minus 12. So we're between minus 6 and minus 12 when we reach 3. And at 3, we now fall off at 40 dB per decade. So that 3 is close enough to the 1 to actually influence the roll-off at 1. 1 would probably, if we just had a first order, it would be at 0.707. But because that 3 is really kicking in before 3 in actuality, this guy might do something more like this. in an actual curve. So our 3 dB frequency is much lower. So that's really not what we want, is just to start building. We want a more effective way of introducing orders to create these, and the Butterworth transfer function for all orders in terms of its magnitude has the following structure. If we look at h of j omega's magnitude, it's going to be 1 over the square root of 1 plus omega over omega c, where omega c is our cutoff frequency. That's 1 in a normalized filter, raised to the 2n. And this is for an nth order filter. That's the magnitude of our transfer function. You pick an n. If somebody says, I want a third order filter, this is what the magnitude would look like in for Butterworth poles. Now we have to figure out, where are these Butterworth poles? I haven't told you. The first one, for a first order filter, I think you can guess. But I want to give you somewhat of an intuitive way to think about where these Butterworth poles are, or where they live, or how I can sort of imagine them. You can find these in table 15.1. But for us, let's just sort of create our own table. Let's say this is the order. That's little n. And now I'm going to, I've already told you that we want all of these poles to be how far away from the origin if we have a normalized filter. A normalized is we have a bandwidth of 1 radian per second. All of these poles need to live 1 away from the origin. So you could now get out your compass, adjust it to have a radius of 1, and draw this circle. And now you say, okay, now I need to sprinkle poles on that circle. And now I'm trying to tell you how to sprinkle them on that circular arc. That's by means of this angular separation. By this, I mean we're going to split our circle that has a radius of 1 into that many pieces, 360 divided by 2n, which means that once we've separated these poles, we can actually look at their pole pattern in the complex S-plane, and this will actually give us poles in the right half plane. Those aren't stable, so we're just going to neglect those and only keep the half that are in the left half plane. So to build up our filter, we would discard all of the poles, and now we're tweeting again in the RHP, in the right half plane. Meaning, if I now said we had a filter, a first order filter, now we're going to do some hard math. We're taking 360 degrees and dividing by 2 times n. N is 1. What's the angular separation between the poles? 180. Yes, right? So now we have 180 degrees. If I now have if I have my circle, and I have 2 poles now, and they're separated by 180 degrees, and I want half of those in the left half plane and half in the right half plane, where are my poles going to be located? This is my S-plane plot. There's my unit circle, radius. Where are my poles? If they're separated by 180 degrees and I want 1 in the left half plane and 1 in the right half plane, 1 and minus 1. And which one am I keeping? The 1 and minus 1. And so there's my transfer function, 1 over S plus 1. We've already talked about that. What happens when n is equal to 2? Now these poles are separated by what angle? 90. And I want 2 poles in the left half plane and 2 poles in the right half plane, meaning I can't have my poles on the axis. If I put 4 poles on the axis, I would have if I put 1 pole on each of the 4 axes, I would have 4 poles, and they would be separated by 90 degrees. But 2 of those poles would be right on the imaginary axis. And what happens when you have poles on the imaginary axis? It's just an oscillator. So it just shakes. So we need 2 poles. That's looking at dance, if you were curious. So we now have 2 poles in the left half plane, 2 poles in the right half plane, and they're separated by 90 degrees. Where are they going to be? They're 1 away from the origin. That would have been an okay answer. But if we started with them on the axis, and that's not working, can't we just rotate all of them? And if we rotate all of those 45 degrees, they still all remain 90 degrees apart, and I now have 2 in the left half plane and 2 in the right half plane. So that I now have this picture. You have a pole here, a pole here, a pole here, and a pole here. Where this the distance away from the origin is 1. This angle is dividing the distance between them, and what did we calculate the angular separation between the poles was? Pointing at my screen like you can see that. Everybody saw my finger on the screen, right? So this must be 45 degrees, and this is 45 degrees, so that the total distance between those is 90. Does everybody see where that's coming from? And you can calculate those pole locations. They're at minus 1 over the square root of 2 plus and minus j the square root of 2, 1 over the square root of 2. Now you know how to design a second order low-pass filter that has Butterworth pole patterns, and they have a bandwidth of 1. And their curve is looking more like that red than, well, it's between the blue and the red. What about 3? The third order. What's the angular separation now? We now have 6 divided into 360. These are 60-degree separation. And now we have an odd number of poles in the left half plane and an odd number in the right. And when you have an odd number, one of those is always on the real line. And you know where to put that one because it's a unit distance from the origin. You always have a pole at s equal to minus 1 when you have an odd number or an odd filter order. These are the easy ones. We now know that we have a pole right here, and that's a distance 1 from the origin. And we just computed that all the other poles are 60 degrees away from that. That's their separation. Which means that now this one is going to be at 60 degrees. This one, need to give myself a little bit more room. This one's at 60. This one's at 60, 60, and 1. But we throw those away. But we have 6. We just keep 3, the 3 stable ones. And this distance, this angle is 60 degrees. And you can calculate that to find the actual locations for those poles. Is this clear? Let's do one more. Let's do a fourth order. Now how far are they separated? 360 divided by 4 is 90, and I split that, that's 45. So these are now 45 degrees apart. And what do we now know? How many total poles do we have in this constellation? 8. 4 are in the right half plane, 4 are in the left half plane, and they have to be all 45 degrees apart, which means we can't have any on the real line, but they're 45 degrees apart. So we would start, let's say, if we started with one on the real line and then we said, let's move that until we're now uniformly or symmetrically distributed, we actually are going to go up 22 and a half, or half of 45. So we go up 22 and a half to get the first one, then we go 45 from there. Or we could do it over here. We say, oh, here is 22 and a half, and here's 22 and a half, so that their total separation is 45. Then we go 45 here and 45 here to get that. Is that? And how far away are these poles from the origin? A distance of 1. So this distance, or that angle right there, is 22 and a half. This distance, or this angle, is 45. Is that clear? If we had a fifth order, what would we do? We would have 1 on the real line, and then we would have 2 up in the second quadrant and 2 in the third quadrant, and they would be the appropriate 36 degrees apart, 360 divided by 10. All right, so now you know how to create Butterworth filter pole patterns. Right? Now after today, you can design a Butterworth filter. You know the pole patterns. You know how to... So let's design those. Butterworth filters. These filters provide a flatter pass band. Maybe I should... This is our pass band, and this is the stop band. If my terminology, just to develop terminology. These Butterworth filters provide a flatter pass band magnitude curve than earlier low-pass filters that we've discussed so far in this class. Let's now look at a particular circuit that we might use to realize a filter, a Butterworth filter pole pattern. And it's going to be active, which means we have an op-amp. Here's our feedback path. Then let's say that we have a capacitor there. We have a resistor there. Whoops. Be careful. I'm not doing this. So now we had feedback there, but now we come to the non-inverting terminal, and this comes down The resistors are the same numerically, but the capacitors I'm going to have to choose to be different values. So I have one as C1 and one as C2. And this is coming to us from figure 21 in the textbook. What's that filter order? Second order. We have two energy storage devices. What's the transfer function? H of S. And you should be able to derive this. Hint, hint. Right? You could do some node voltage analysis to find this transfer function. If you did, you would find the numerator is 1 over the product of our capacitors. The denominator is S squared plus 2 over C1S plus 1 over C1, C2. And what happened to our resistors? I just went ahead and set those equal to 1. So now we have the ability to adjust these two coefficients in the denominator by the appropriate choice of our capacitors, C1 and C2. And this is, if you now had to say what that transfer function was giving you, you've already told me it's second order. Is it low pass, band reject, or high pass? Can you tell me, knowing what you know about Bode plots and just a generic back-of-the-envelope sketch, do you have any zeros, finite zeros? No, so you're not going to be sloping up ever, are you? What's the DC gain? 1. What are you doing from that DC gain? How are you moving? You're always decreasing, aren't you? The denominator is always getting bigger. So this is low pass. This is a second order low pass. And we want to pick the C's to give us a Butterworth pattern. So this is the second order stage that we will use for all of our different second order pieces of the Butterworth filter patterns. Meaning, if we had a fourth order filter, we're going to have two second order pieces. Because we had a fourth order filter, we have 4 complex poles. We're going to have 2 complex conjugate pairs due to the ones that are closest, and then those further ones give us another complex conjugate pair, and those will correspond to 2 different polynomials in our denominator, and this second order section will allow us to realize those 2 different polynomials. How do we do that? Well, if we normalize that transfer function, we could say it's now S squared plus B1S plus 1. We've now made the bandwidth 1 by setting that constant equal to 1. And by setting that constant equal to 1, our constant terms, we have a constant in the numerator and a constant in the denominator, and they're both the same, 1 over C1, C2. And we've set both of those equal to 1. That now gives us a relationship between C sub 2 and C sub 1. If I give you a C1, you can give me a C2, right? Just like somebody saying, you, A. Now I give you a C1, you give me a C2, right? Just looking. Is everybody clear on that? Now, from the linear terms, B1 is 2 over C1. So if somebody gives me a B1, which they can in a second-order polynomial, then I will find C1 is 2 over B1. And we want to cascade all of these second orders in order to yield higher order filters. Meaning, if I had a fifth order, I would take 2 of these second order pieces and 1 of our first orders and put those together, and now I have a fifth order. And their coefficients would be influenced by all these C's. And then if I wasn't happy with a bandwidth of 1, what would you do? Frequency scale, and you know how to frequency scale capacitors and resistors, and you know how to magnitude scale. That's what we want to do. Now, there's a formula that I'm not going to derive, I'm just going to give you for determining the order of your filter. And you can just use this formula. You have 4 sheets to get it on there. Hopefully you can fit it. And that says the filter order N is minus 0.05. The attenuation into the stop band, that's the A sub S, log base 10 of the stop band frequency over the pass band frequency. So we just need to know omega sub P, omega sub S, and A sub S. And since we are dealing with a ratio of frequencies, if both ratios are in hertz, that's okay. If they're both in radians, that's okay, but they can't be a mixture. I'll show you in a picture. The question was, what are these omega sub S and omega C? And let me just say that this approximation, you can just assume that it's okay in this class, but this approximation is good when the attenuation we want in the stop band is such that 10 to the minus 0.1 A sub S is much bigger than 1. Where the A sub S is in units of dB. And if we look at that, then much bigger is essentially saying that we want A sub S to be much less than minus 10 dB. And if somebody says, I want minus 12 dB down when we reach omega sub S, then you can use this approximation for finding the filter order. Let me draw what we mean. Here is our pass band, and there's our stop band. Here's our minus 3 dB frequency, and that's occurring at omega sub P. There's the pass band frequency. That's the definition of omega sub P. And then we have this, A sub S, in dB, so that would maybe be minus 26, let's say. And that now tells us how much attenuation we need by omega sub S. This is the pass band, that's the P, and the S is for stop, or stop band. Or you can think of this as our cutoff frequency. Let me give you an example. Suppose that somebody says your pass band frequency is 2,000 hertz. And they want an attenuation, A sub S, of minus 16 dB at a stop frequency of 10,000 hertz. is that a decade beyond the passband? No. It would need to be 20,000, wouldn't it? If it was, and then we could say, oh, maybe we just need a first order. A first order filter would be minus 20 dB, a decade beyond 2000. That's not really going to check it or meet our specs. What we have now in terms of specifications, this is now our F sub P, and this is our F sub S. And we want this point to be minus 16 dB. That's our A sub S. And we said our approximation was good as long as A sub S was smaller than minus 10, so we're okay there, but we could check that. We could say check. If we looked at 10 to the minus 0.1 raised to the minus 16, that's now 10 to the 1/10 of 16 is 1.6. Now what's 10 to the 1? 10. What's 10 to the 2? 100. So we're somewhere between 10 and 100. If we compute this, we would find that that's 39.8, and we're saying that's much bigger than 1. 40 is bigger than 1, and that's okay. So what's the filter order? If we use our formula, the formula says that the order of our filter is little n, which is minus 0.05, times A sub S, which is minus 16, times the log base 10 of 10,000. And since we were both in hertz, we can just take their ratio. We don't have to convert those to radians per second, divided by omega sub p. We get 1.14. Can you build a filter that's 1.14 in order? Can you have a 0.14 of a capacitor? No, you can have one capacitor, two capacitors, three capacitors. So they only come in integer amounts, don't they? These energy storage devices. What size of a filter do we need then? We need 2. Give me a 2, right? So now we need n equal 2 to achieve that specification. Yes?
Why don't we just like round out one?
The question was, why don't we round down to 1 instead of going all the way to 2? That's for you and your boss to decide. So if you go into your boss and say, well, it's really demanding a little bit more than a first order, do we want to spend the expense of getting a second capacitor to get the attenuation we want? You're obviously going to more than meet the spec if you go with a second order. You're not going to achieve the spec that you had with the first order. So your boss says, we have to meet the spec. You go, okay, then we need 2 capacitors. Okay, so now you would need to implement this circuit instead of a first order circuit. Let's write down the steps for a Butterworth filter design, and I may offline have to give you a third order. Or do I just, well, let me write those down. I can do that in the remaining time. Here is a low-pass Butterworth. Here are the steps. First, you determine the filter order, and I hope that you now all know how to do that, given the passband frequency, the stop band frequency, and the attenuation between those. So determine the filter order. In the last example, we determined that we needed a second-order filter. Then what you need to do is find But you now know for a second order where the poles are. In a normalized design, you know they are at this 45-degree angle. They're at minus 1 over the square root of 2 plus and minus j, the 1 over the square root of 2. So now you find the normalized denominator. If it's bigger than first or second order, then you can look at the table to find the normalized denominator polynomial. In table 15.1. Then what you do so let me sort of talk this through with an example. You can keep writing. No, I would just listen because I'm out of time. But let's say this is a third order. Now you combine that second order section with the first order section. You need to determine these R's and C's in these different sections. In the first order section, you know it's S plus 1, so that means your R's and C's are all 1. In the second order, you have a different set. You have S squared plus S plus 1. That gives you those 45-degree angles. That determines your C's, and that now gives you a low-pass third order with a bandwidth of 1. If you wanted to change the frequency, then you can change that to, let's say, 200 hertz. Your frequency scaling is 2 pi 200 over 1. And then your magnitude scaling, let's say that you wanted to use 10 k ohm resistors, and you had 1s in all of your circuits, you now have a magnitude scaling of 10,000. You combine all of those, and voila, there's your circuit. So, I may give you a little bit more, I may fill in the details of this design, the steps, and you're good to go for homework number 10.